We have already discussed what is a non-oriented graph. What is that? There are vertices and without any arrows. Say I have given these are the vertices and there are no arrows involved. That means it is a non-oriented graph. What does it mean? If I have taken two vertices here, P and Q, that means if there is no arrows, from P to Q some flow is possible, Q to P also flow is possible, both way flow is possible. What happens in case of an oriented or directed graph? A single arrow is used. In this graph I am using a single arrow. This means flow from this point towards that point is possible, not the vice versa. Now we are going to see a digraph or directed graph or oriented graph such as this one, where we are finding double arrows are used in some cases, single arrow is used in one case. What does this mean? The double arrow means that the weight of the edge for this particular connection of the vertices is high. If I put the number A here, if I put here B and if I put here C, then I can say from the graph A is much more than B and C is much more than B. This is the meaning. So these are the meanings of the double arrow and the single arrow. Now we will have another variety of graph and which we will see in the biostratigraphic work, semi-oriented graph. Some of the vertices are joined by edges with arrows and some of the vertices are joined by edges without any arrows. Where you are seeing without any arrows, that means both way connection is possible, and where you are seeing arrows, that means one way connection is possible. So it is a mixture of oriented graph and non-oriented graph. We usually join the two vertices by a single line or a curved line. M and N are the two vertices joined by a single line, but there are some cases where the two vertices A and B can be joined by two lines if required. We are going to see complementary graph GC of G. Take a graph like this. A, B, C, D are the four nodes or the four vertices. There are three edges AB, BC and BD. In this case, one can write down the matrix A, B, C, D, A, B, C and D. We will fill up this matrix by 1 and 0. Now suppose we do a transformation on this matrix that 1 becomes 0 and 0 becomes 1, then the graph that we produce is known as the complementary graph. I am requesting the viewers to pause the video and create the GC graph without making the matrix. Just take the 4 points as A, B, C and D. So we see where the vertices are connected and which vertices are not connected. From that, do a complementary operation. 1 becomes 0, 0 becomes 1, and can you draw the complementary graph? It must be done by the viewer and then look at my video. I hope you pause the video, and I can expect many of you have drawn like this. AD is joined, DC is joined, because these were not connected. This is you are going as to say as a complementary graph, and it is not correct, because earlier A was not a loop, A was not connected to itself. So in the complementary graph GC there has to be a loop here. For point B there has to be a loop, for point D there has to be a loop, and for node C there has to be a loop. This is the correct complementary graph. Where there was no loop, loops have appeared. However, note that in biostratigraphy we will come across the complementary graph where these loops will be ignored. Loops will not be presented in biostratigraphic graph. In biostratigraphy, if I draw this A and B, and if I write its matrix A B A B, as per classical graph theory, A is not connected to itself, so I should have put 0, but in biostratigraphy we write here 1, A is connected to B, B is connected to A, and so B is connected to B. This is another way of presentation. Now, starting from a digraph G, we want to give a transformation that 0 remains 0, 1 becomes minus 1 and minus 1 becomes plus 1. Then how the graph will look and what is the physical meaning. 0 alters to 0, which means the vertices which were not connected will not remain connected either. 1 becomes minus 1, that means suppose a flow was happening from here to there, the flow will change its direction. V1, V9, Vx, V2 and V star. So, now arrows directions will be changed and this one. Now, just for a matter of practice, I will request you to write down the matrix for G, and for this graph G dash also write down the matrix M dash. We will do a simple exercise with the digraph with weight. Consider there is a vertex V0 where from several vertices VA, VB and ultimately to Vm, inflows are happening. So, the inflow is represented by such arrows and the weight of this edge is A, the weight of this edge is B, the weight of this edge is M, and from V0 there are many outflows happening. V0 to V alpha the weight is alpha, V0 to V beta the weight is beta, and V0 to V phi the weight is phi. Now, we take a general condition, the number of edges leading to input to V0 may differ from the number of edges leading to the output from V0. That means, if I start counting VA is 1, VB is 2 etc. up to Vm some number, and here we count V alpha is 1, V beta is another, V phi is another, we count the number. These two numbers at the two sides, this side and that side, may or may not match. So, the total input happening to the V0 is given by sum of these A plus B up to M, that is what is written, let us say it is capital A, and the total output will be alpha plus beta and goes up to phi, let that be capital B. Now, the storage or deficit at V0 will be A minus B or B minus A. This symbol means bigger minus smaller. For example, I can write 5, 3 equal to 2, also 3 and 5 is equal to 2, and I can write 5, 5 is equal to 0. So, this symbol means A minus B if A is more than B, and B minus A if A is less than B. If it is a some storage is happening in V0, that means A is more than B, and if deficit is happening, then A is less than B. Now, we start, suppose each flow is increased delta times. So, A will become A delta, B will become B delta, M will become M delta. Regarding the outflow, alpha will become alpha delta, this would become beta delta, this would become phi delta. So, the total input will be A multiplied by delta. This is the A value, each of them are multiplied by delta. So, it becomes A delta. Similarly, the total output will become B delta. So, the storage or deficit will be given by taking out delta as common, delta and then A and this symbol and then B. And now, if we think that all the inputs are added by plus delta I and all the outputs are added by plus delta 0. A becomes A plus delta I for input, and O, this O is for output, which I am also calling as delta 0. So this becomes b plus delta I, this becomes m plus delta I, here is alpha plus delta 0, beta plus delta 0 and phi plus delta 0. So the total input will become, if I add up a plus b up to m, that has been done, plus delta I coming so many times, say it comes y times, and the total output likewise will be alpha plus beta up to phi, and then suppose it appears z time, then z multiplied by delta 0. So the storage or deficit at V0 will be, now this is capital A and this is capital B. So A bigger minus smaller, B plus y delta I, and then this symbol z delta 0. Now note that if y is equal to z and if delta I is equal to delta 0, then it will equal to A bigger minus smaller, A this symbol and then B. So the storage or deficit at V0 will remain the same as our first case. If y is equal to z, that means the number of edges joining V0 leading to inflow is equal to the number of edges taking the flow out, that is condition 1, and second, each of the increment in the inflow and outflow are maintained the same. There is also another possibility when this remains the same, simply when y delta I is equal to z delta 0, y not equal to z, that is also possible. Here y and z are the whole numbers. So just to give an example, 8 multiplied by 4 is equal to 16 multiplied by 2. Here 8 can be y, that means 8 number of edges are there. There are 8 edges through which V0 input is happening, and here this 16 is the number of edges through which the outflow is happening. These are the outflow edges. So this can be z. Then what is 4 here? This 4 can be the delta I, that means whatever were the A, B, C values, I was adding up here 4, 4, 4 etc., and here 2 is equal to the delta 0 value. What is that? Whatever be the value of A, B and M etc., delta I was equal to 2. So in this case also it remains equal. Let us look at a few terms related to biostratigraphy and slowly we will link them with the graph theory. Maximum horizon, what does it mean? It is a horizon where the set of coexisting species is maximum. So in the geological time scale, a part of it is being shown from T1 to T2 time, the Younging direction. Suppose within this range of time T3 to T4, a set of coexisting species and their number is maximum, then this zone is known as the maximum horizon. We will see similar concept in biostratigraphic definitions. Once we say coexistence, there are two types of coexistence. One is called actual coexistence. What is that? Two species actually coexisted if they occur together at least in one section. For example, in this time range, say this is the range when species A was there and this is the range when species B was there. So they have coexisted within this time span and it is found in at least one section. So we call such coexistence as the actual coexistence. In some cases, we find an apparently anomalous thing. Within T1 to T2 time range, we are observing in one section P1, species A appears and then it disappears, then there is a time gap and then species B appears and then it disappears. And in section P2, B appears first, is observed, and after that A is observed. One possibility is that of such anomaly. So, here what is happening, it appears this is the situation and here it appears this is the situation, younging and old and younging. How this can be explained? One of the possibilities is that A and B coexist, but here A is not found due to preservation issue and here A is not found due to preservation issue. Here B is not found due to preservation issue. So, that has also to be established, but there are cases where such P1 and P2 sections have been documented in terms of species. Although here we have used the word species, it can be better to use the word taxa, more general term, and here also instead of coexisting species we can use the word taxa, and I have already explained what is the meaning of taxon and taxa. Now, we will see another kind of coexistence, that is known as the virtual coexistence. What is that? If because of ecological factors or due to inadequate documentation, the coexistence is not actually found, that means no single section is available where in the same horizon the taxon A and taxon B are found, then also there is a chance that they virtually coexisted. How that is understood, we are going to see in two examples. In one example, we are finding X taxon ranges this much time and again this much time, and here is a gap, whereas Y is continuous. So, here X might be absent due to either ecological factor or due to inadequate documentation, maybe geologist has not properly documented. So, in such case we say that X and Y coexist, and this is known as the virtual coexistence. Now, I will look at two sections P1 and P2, and what I have explained just now, that is a case of the virtual coexistence. Two species are compatible if they actually or virtually coexisted during a part of their existence. It is important, a part of their existence. This has to be understood very clearly. Coexistence does not mean that taxon A appears here and disappears there, and taxon B also shows the same thing, not necessarily. This is possible A, B, or this is possible A, B, or this is possible A, B, or this is also possible A and B. So, a part of their existence they were together. What is the time or common domain? This is the common domain, here this is the common domain, here they are like that, here this is the common domain, and here that is the common domain. So, we say that the two species, or here again we can replace, instead of species we can call taxa. Two taxa are compatible if they actually or virtually coexisted during a part of their existence. We will now define the term neighborhood. Neighborhood of a species X is all the species compatible with X. Again here we can replace the word species by taxon if required. Suppose these are the species that coexisted or are compatible X, Y, P and Q. That means at least a part of geological time they were occurring together. In this case, neighborhood of X is Y, P, Q. If we find there is a species M, and when M is occurring no other species is occurring, then we write neighborhood of M is the null set. So, if the neighborhood is represented by a null set, that means that that species occurs alone. When it was there, no other species was found. I have given the distribution of species in time wise manner A, B and C. So, when C is occurring, no other species are found, therefore, the neighborhood of C will be a null set, and the neighborhood of A or the neighborhood of B is not a null set. So, I can write, if we give a symbol, neighborhood of A is not a null set or neighborhood of B is not a null set. Now, how the neighborhood is represented in the graph theory? Vertices connected by edges are the neighbors. For example, in this case x, y, p and q. Since they are the neighbors, so I will join all the vertices. That means there was at least one common duration of time when all of them were existing together. Suppose I draw this graph x, y, p and q and I join like this. What does this mean? There was a time when x and y was together on the earth. There was a time when x and q were together. There was a time when p and q were together, but there was no common time when y and q were together. There was no common time when y and p were together. How to demonstrate? So, here I have drawn the situation. X and y for some duration of time existed together. So, that explains this edge. X and q for some time existed together. So, that is this edge. P and q for some time existed together, and as you can see x and p never existed together. Here is x and here is p. There is no common time. Therefore, x and p are not connected by an edge. Similarly, q and y is not joined by an edge. This is q and this is y, and there is no common time span. So, in this way the edges and the vertices can be used. There can be other uses also. Do not think that this is the only use of the edges in biostratigraphy. We will see varieties. Now, what was explained can be given a more common symbol. The set of neighbors of vertex x is denoted by this symbol. So, the neighbors of x of vertex x is m, n and p. X and p are connected, p and y are connected, but that does not mean x and y are connected. So, in terms of symbol I can write this as this. So, now I would request you find out these expressions. Now, we are going to see oriented graph in biostratigraphy in one sense. Different authors might use the oriented graph in different senses. So, what we are doing here is the standard one, but in the research papers, before looking at these graphs, you must look at how the author has defined the oriented graph there. The oriented graph consists of an ordered pair of vertices. These words are coming, ordered pair, we will understand, and these pairs are known as arcs. Let us see. Suppose I write two vertices u, which is x comma y. Here we mean that species x lies beneath species y. So, in the succession this would be the form x lies below species y, x is older, y is the younger species. This is one possibility, but it may be the case that this can also be found in the rock record, and it is known as Lazarus effect, which means due to the depositional environmental change x got disappeared in the vertical section. So, here it does not mean that from this part y is older than x, and contradictorily here x is younger than y, that is not correct. So, there are such sections where merely above does not mean younger, and in that case it will not mean older, it will not mean younger, but commonly yes, younger, older in this sense will work. Also note, once I am writing x below, it does not mean y developed by evolution from x, I do not mean that, and therefore, this does not indicate a speciation. Now, if we invert the sequence due to our improved understanding, then u dash will become y comma x. What does this mean, inversion? Say we were interpreting the lithological record from this vertical section A and B. So, we were initially thinking this is the top younging direction, we were thinking B is younger than A in absence of any geochronological dates available, just on the field observation. But later we found some critical observation in B that questions whether it is really younger. For example, if mud is desiccating in open air, it produces concave upward joint. This concave upward is towards the skyward direction. This can be called sun crack or mud crack, commonly found in marl, in mud, in fine grained sediments which is exposed to sun, which had got some water, and that water evaporates, and after that this concave of geometry is produced. Now, in the geological record, suppose here we are observing sun cracks or mud cracks of the past which are oriented in this way. This immediately tells us that this was not the original orientation, it cannot be, rather this was the case. When B was deposited, mud cracks were produced, then it got filled up by some sediment, and then everything took a turn. Is there any geological example where such turn happens? Yes, in case of certain recumbent folds or the neutral folds what I have drawn which is closing sidewise. Say this was the original layer, now a folding happens, so this gets turned and that gets turned. So, what happens here, the younging direction which is here, follow this line, it comes here. So, as if younging goes down and this older material, if you follow it here, it comes over there. So, an inverted sequence is produced. It is not uncommon in nature. So, in such a case, suppose we wrote u x comma y based on our first observation of the fossils which is at the top, which is at the bottom. Later when we invert the sequence to get the original disposition, then we might change u to u dash, and then x and y interchange their positions, it becomes y comma x. If required, we can do that. Now, we will put two symbols, plus and then x will indicate set of species found above x, and this minus and x will mean set of species found below x. Now, I am going to give you an example of this. I am looking at a vertical succession of taxa n, m, q, x, y, z and p. Commonly this is a younging direction, it is not an inverted sequence. So, here if I give this symbol and z, then above z lies p, so p is the answer. If I give this symbol and m, above m what lies, q, x, y, z and p, that is the answer. And if I give this symbol and p, that means at the topmost we have nothing above it, so a null set is given. Similarly, this symbol and z, it will give y, x, q, m and n, and this will be a null set because below n nothing lies. What we observe is that these are subsets of